Hello, hello. So today we are talking about confidence intervals for means. Remember, means are mu and x bar, not proportions. So today's all about means and how we make an interval to estimate averages for a population. So we're going to start off today with the key point number 1. So the key point says for each problem, the population is the who we took a sample of. So population is the who we took the sample, but the parameter is the what we're measuring or what we're estimating about that group. So this is actually the state step. This is the state step in our 4-step process. So this is my 4-step process. It says how to construct a one mean interval. And remember, these 4 steps are the same for every interval that we make. It always starts with the state, which is the population and parameter, then the plan, which are my 3 conditions, and the main condition that's going to change, it's already underlined for us, but the normal condition. This condition is the one that changes depending on the type of interval we make. Then we have step 3, which is the do condition. This is where I actually do my calculations and my formula is in this step 3. And then I conclude. So I always conclude using that template. We are blank % confident that blank. So we're going to take a look at this example, and we're going to use this example the whole time. So if you want to write down this example or at least get down the symbols, that's going to set you up well for success. So it says a steel milling machine produces steel rods that are supposed to be 5 centimeters in diameter. When the machine is in statistical control, the rod diameters vary accordingly to a normal distribution, so keyword right there, normal, it tells us in the problem, with a mean of mu equals 5 centimeters. However, you believe that the machine is not working properly. So it's supposed to be this, but we think it's different. So we take a random sample of 150 rods, so n equals 150, and it has a sample mean diameter of 5.005. So this is my x bar, my sample mean, and a standard deviation from the sample of 0.02. So this is my SX. So we want to construct a 90% confidence interval for the true mean diameter. So if we start with the state step, the first thing we state is who is the population. Well, the population comes from who I took a sample of. It says I took a sample of 150 rods, so the population is all steel rods or all rods produced by this machine. So population, all rods produced by this machine. The parameter is the what are we measuring about the rods? Well, if we look back at the problem, we're looking at the rod diameters. So the parameters we want to estimate the true average diameter for each rod. So population is the who, it's all rods produced by this machine. The parameter is the what are we measuring, and we want to estimate the true mean diameter for the rods. So the plan step, we talk about my 3 conditions, random, normal, and independent. So the new one is this normal condition is now going to be a little bit different. For means, the normal condition is either going to be stated in the problem, or we can apply the central limit theorem that says my sample size is greater than or equal to 30. Random and independence are the same as before, so let's take a look at these in context of the problem. So it's the same problem. If I do the plan step, the first one is random. Well, it says we took a random sample of 150 rods, so it's stated that it's random. Check. So that's all you have to do for the random step. Just say random, stated. If you want to give the annotation, that helps. but this is all I and the AP reader are looking for. The next one is the normal step, so normal. Well, if you look back to the original problem, it is stated that it's normal, but we could also use the central limit theorem. It says we took a sample of 150 rods, so central limit theorem. And you can say 150 is greater than or equal to 30, check. So if it's stated normal, just say stated, check, and annotate where that is in the problem. Or we can use the central limit theorem because my sample is greater than or equal to 30. Last but not least, independent. We are going to assume they're independent rods, so assume that one rod does not change the other. So assume independent rods and that the population of rods is at least 10 times 150. So we're going to assume that they make more than 1,500 rods on this machine, which is a safe assumption. If we're at a big plant and they're making all these rods, we can assume that the population is at least 1,500. So how do we actually calculate the interval? How do we do the do step? So all confidence intervals, remember, follow this form, the point estimate, and we said the point estimate is either x bar or p hat. Well, today we're talking about mean, so it's going to be x bar, plus or minus the margin of error. And this formula changes depending on the type of interval. And the formula that we're going to use for a one mean interval is this formula below. So this is for one mean, meaning I'm given one mean in my problem, or one x bar. So make sure you get this formula down, and we're going to break it kind of into pieces. The first piece is this x bar, and x bar is the sample proportion, sample mean, sample mean. So x bar is the sample mean, it comes from the problem, plus or minus the critical value times the standard error. Remember, we call this whole piece the margin of error. Well, what is T star? Excuse me. What is T star? So we talked about Z star last time, but now we have T star. T star is a critical value that we use for confidence levels for means. So instead of Z star, now we have T star, but it's essentially the same idea of this critical value that determines the width of the interval. And then I multiply T star by the standard error or standard deviation of the sample. You probably remember it as sigma over the square root of n. Well, I don't have sigma. I have the sample standard deviation, or Sx, is divided by the square root of n. So this is the big formula. This is how I find the actual interval after I do steps 1 and 2. But before we plug our numbers in, let's take a look at T star and see how do we find this. So T star is found on the T distribution table, or that purple sheet. You guys got a purple sheet? This is the purple sheet. And T star is found in one of these rows. So all these numbers right here, these are all different T stars. And T star is a critical value. The bigger my confidence gets, the bigger my critical value gets. So if I want to be super confident over here, T star is going to be giant. If I'm okay being like really little confident, it's going to be a small number. So T star gets bigger with my confidence. How I know which row to use comes from this thing called degrees of freedom. So DF is degrees of freedom, and it's the sample size minus 1. So df equals n minus 1, and that's my second key point. So the degrees of freedom, df, is the sample size minus 1. If you want to write that formula again, df equals n minus 1. And it tells us which row we use on the t-table. So for example, it will say what is the t-star value for 95% confidence interval for a sample size of 20. Well, if n equals 20, my degrees of freedom is 20 minus 1, or 19. So if I want to find my t-star value, I'm going to go to row 19, and it's going to be one of these t-star values. Well, in order to know which t-star value to use from the row 19, because that's my degrees of freedom, I look for 95% confidence on the bottom, which isn't shown, but it's actually this one right here. So on your purple sheet, you see the confidence level. So 95% confidence would be down here. And that matches with row 19 for my degrees of freedom to give me a t-star value of 2.093. So that's one example. Another example could say you want to compute a 90% confidence interval for the mean of a population with an unknown population standard deviation, so a lot of kind of context. The sample size is 40, so n equals 40. What is the value of t-star you would use for this interval? Well, if n equals 40, then my degrees of freedom is 40 minus 1, or 39. But if you look at your table, there is no 39. It just goes 30 to 40. If your degrees of freedom is not on the table, you go to the next lowest one. So I would end up going down to 30. So I look in that 30 row and match that with 90% confidence. So my t-star value is 1.697. So this is how I use that purple sheet to find t-star. Now let's go back to our problem. So you take a random sample of 150 rods. So if we annotate that again, n equals 150. And it has a sample mean diameter of 5.005. So x bar is 5.005. And Sx, or the standard deviation, is 0.02. So if I want to make my interval, it follows the form x bar plus or minus t star times s over the square root of n. Well, if I plug in my numbers, 5.005 plus or minus t star. Well, if I think about t star, n is 150, so my degrees of freedom is 150 minus 1, or 149. Well, if you look at your sheet, there is no 149. It just goes to 100. So if you look at where 90% and 100 meet, you get 1.660 for t-star. And then I want to times that by s, which is 0.02, over the square root of n. So I plugged in x bar, which I got from the problem, plus or minus t star, which came from 90% meeting 100 degrees of freedom, because there was no 149, times s, or the standard deviation of 0.02 over the square root of n. When I do these calculations, I'm going to get 5.005 plus or minus 0.003. So how I got that 0.003 came from doing this arithmetic. Well, this is kind of like the interval template, but if I really want to make the interval, I need the lower one and the upper one. So 5.005 minus 0.003 gives me 5.002 to 5.005. 5.008. So this would be my interval. I am 90% confident that the true mean diameter is within the interval 5.002 to 5.008. Let me write that out for us so we have a formal conclusion down here. So this is my conclusion. I just typed out what I said. We are 90% confident that the true mean diameter, so I have the context of the problem, of the rods is within the interval 5.002 to 5.008. I have to have this step in order to have a complete answer. I can't just end it here. I have to interpret what this interval means in regards to 90% confidence. So that's a wrap. We construct confidence intervals using the state, plan, do, conclude steps. And T-star is found using the T-distribution with degrees of freedom n-1. And T-star determines the width of the interval. So this is section 8.3 in your textbook. Please go there for more examples and to do some of the homework problems. Thanks, and I'll see you later.